Here's the self-test solutions. You'll find that the future value and present value formula are roughly, well, they are the same formula, just rearranged. And the first five are future value problems for the most part. The next five, mostly present value formula, but again, same formula, just rearranged. So taking a look at the first, $10,000 invested for 40 years and earning 10%. So in your formula, 10,000 times 1 plus r, so 1.1, that's 10% added to 1, 40 years. If you do it in the calculator, it looks almost the same. 40 years invested at a rate of 10%. In your calculator, you'll just put in the whole number 10. The 10,000 is an input to your calculation, so it's money going away from you, entered as a negative. No other cash flows, payments are zero, and answer is the same. The second one, 300,000, growing at 2% for 20 years, and then declining at 1% for 10 years. So it's two problems. We've got the 20 years, 2%, 300 million, excuse me. So we'll just put in 300. That number, the 446 million, becomes an input to the next part of the problem, where you have 10 years of a negative 1% rate and no payments again. Now, it's easier to do this way with the formula because it's just chain multiplication. It's 1 plus r to the 20th year, 102, and 1 plus r is negative, so it's 99% instead of 1.0, which is 100%, to 10 years, so 403 million. Number 3, a beach house bought in 1957 for 50,000, sells 60 years later for 500,000. Plenty of heard stories like that. The formula, if you just slightly rearrange it to solve for just rate, future value divided by present value, raised to the 1 over number of periods, minus 1 equals rate. Calculator does it much easier. You've got, what, 60 years. Solving for rate, so we want to put in our input, 50,000. No other cash flows. 500,000 is a positive coming back to us. 3.9%. The next one, how long does it take to double your salary if your salary grows 5% annually? That one, you can do it either by guessing, just keep plugging in the unknown number of years, or you can take the natural log of this expression. What you'll get, since you're doubling, what you start with is 1, you end up with 2. So taking the natural log of 2 equals that exponent, number of years, times the natural log of 1 plus r. Calculator does it much easier. 5% rate of return. Input is 1. Output comes back to you plus 2. No cash flow in the middle. 14 years. My calculator rounds that up to 15. You wish to deposit money today so that in 45 years you'll have 400,000. So this is now solving for the beginning of the time period, given that you know the end of the time period, 400,000. So we could just plug into either formula and solve for the unknown, which would be PV. Here, 400,000 divided by 1 plus r to the t. You get about 8,276. R, we said, was 9%. And we're trying to reach, what, 400,000 at the end. I guess we need to format this a little better. And same answer as the formula. The next one, you know the value of the car in 1990. They want to know the value of the car before that, 1980. So you have a future value, what you know. Again, we're not worried about any other sorts of cash flows. 10 years, 6%. And again, we'll need to reformat this. The next one, number 7, say future value, just comparing rates of return with annual versus monthly compounding. In the annual, simple, just like the earlier problem, start with 10,000, 1 plus R for 20 years. And you get about 115,000 in value. In the second one, monthly compounding, you want the rate and the number of time periods to agree. So monthly compounding requires a number of months over a 20-year period. 240 months. The monthly rate is not 12% annual, but instead 1% per month. And same input. The 13% is the better choice. The second choice, had it been 12.3% compounded monthly, that would have been the better choice. So that's compounding. Here's Warren Buffett with quarterly compounding, trying to set aside $1 million 10 years from now. 8% annual rate, quarterly compounding. 8% annual on a quarterly basis is 2% per quarter. 8 divided by 4. 10 years is how many quarters? 10 times 4, 40 quarters. So I always want an agreement between number of periods and rate. And so if you input it this way in the calculator, break it down to period rate, number of periods, your calculator will give you the same answer as the formula. The other way to do it is to switch your calculator back and forth between number of payments per year as being 12 if it's monthly and 4 if it's quarterly. But if you just leave it set 1-to-1 correspondence, which was the problem here, you'll sometimes forget to change it back. So anyhow, 40 quarters, 2% rate, grows to about 452 that you need today, which is less than 463 that you need today to reach the same goal. Why? You need less because there are more frequent compounding, 40 times versus 10 times. And annual rate, well, we're dealing with a problem that works in months. So the way to solve for rate, same way, take the formula, rearrange it, FV divided by PV, raised to the 1 over number of periods minus 1, gets you a monthly rate, multiply by 12, gets you an annual rate. We can let the calculator do it. I'm going to triple money. So if I put 1 in, I'm going to get 3 back. I could use any numbers there as long as it's a tripling. And you'll see that your monthly rate's about 0.3%. Your annual rate is about 3.7 or 3.67%. And all that is taking the monthly and multiplying by 12 to get to annual. So that's a little bit of compounding, a little bit of present value, a little bit of future value. And as long as your calculator is set up where it's 1-to-1 payments to compounding, you should get these answers when you put this in. As I say, the calculator is different from the formula in this column right here. It takes just the whole number. You put in a 2, as opposed to when you're working with the formula, it's decimal, right? It's 0.02. And that's future value, present value.